We humans, we just love the biggest, the tallest, the oldest, Like, give us the highest mountain, the deepest ocean trench, and we're all ears, right?
Oh, yeah, absolutely. We are drawn to those extremes.
And when you think about it, that fascination definitely extends to the Earth itself, like the ground beneath our feet. Especially when we're talking about age. Like, we've all probably heard about that at Cast and Ice up in Canada, right?
Right.
Holding that title of the world's oldest rock. But it got me wondering, what about the U.S.? What's the oldest rock we've got here?
That's a great question, and it seems pretty straightforward, right? But as we're going to explore today, the answer, it's a lot more complicated than you might think.
Yeah, that's what really intrigued me when I was diving into the stuff you sent over, especially that GSA Today article, USA's Oldest Rock, a simple question with a complex answer. It really highlights how much detective work goes into figuring this out.
Oh, for sure. It's real geological detective work.
All right, so a good place to start, I guess, is with a spot that many people might already think of when they think ancient rocks, and that's the Morton Gneiss in the Minnesota River Valley. I remember even reading back in 1975, there was a sign there proudly proclaiming it the oldest rock on Earth.
Wow, that's bold.
I know, right? And the article mentioned how it's got this sort of messy appearance. Like, being someone who's not a geologist, I have to ask, how do you even begin to figure out the age of something that looks like it's been through the ringer multiple times, with all these different events layered on top of each other?
Well, that's really the fundamental challenge when you're trying to understand these rocks that have been around for billions of years. They've often experienced multiple episodes of intense heat and pressure, squeezing, folding, all sorts of alteration. And all of that can really make it tough to see their original formation age.
Yeah, that makes sense.
And this is where geochronology comes in.
Geochronology.
That's the science of dating geological materials. And, our ability to do this has really advanced a lot over time, especially with these really ancient rocks.
So going back to the Morton Gneiss, how did scientists first try to figure out its age? And what were the limitations they ran into with those early methods? The article mentioned some of the initial attempts.
Right. Well, early on, one of the techniques they used was potassium-argon dating, or KAR dating. And this was often applied to minerals like micas, which are common in many rocks.
Okay.
And this method, in the 1950s, it actually suggested an age of about 2.4 billion years for the Morton Gneiss.
2.4 billion. Still pretty old.
Oh, incredibly old. But the problem, as researchers like McDougall and Harrison pointed out later, is that these minerals, these micas, they can lose a lot of their radiogenic argon, the argon that's produced by radioactive decay, at relatively low temperatures. We're talking just 300 degrees Celsius or so.
Oh, wow. I wouldn't have thought that was that low.
Yeah, and when you consider that these rocks have been heated and squeezed over billions of years, this method just wasn't accurate enough for these really, really old rocks. It's like the clock was being reset, so to speak.
Okay, so the ages they were getting were actually younger than the rock truly was because some of that argon had leaked out over time.
Exactly.
So what came next in this quest to date these ancient specimens?
Well, by the second half of the 20th century, the scientists had made some real progress, and rubidium-strontium dating, or RBSR dating, came into play. In the 1970s, they applied this to the Morton Gneiss.
Oh, right.
And they got an estimated age of about 3.55 billion years.
Okay, that's getting closer to that 4 billion mark we're talking about, right?
Right, but the thing with RBSR dating is that they were analyzing whole rock samples.
Oh, so like a big chunk of it.
Exactly. They were hoping to average out the ages of all the different minerals in the rock. But as researchers like Field and Roheim have pointed out, these ages, they were often geologically meaningless.
Meaningless.
Yeah, because you're analyzing this mixture of materials that could have formed at all these different times, so you get this kind of blended, blurred age that doesn't really tell you the true age of the rock itself.
So both of those methods, they kind of lack the precision to really disentangle all that complex history locked away in these rocks.
Right.
And this brings us to zircon, right? This amazing mineral that the article called the queen of geochronology, which is high praise. What makes zircon so special for dating something so incredibly old?
Yeah, zircon is pretty amazing. Chemically, it's ZrSiO4, zirconium silicate, and it's really the gold standard for dating ancient igneous rocks, mainly because of a few key properties. When zircon crystallizes from magma, it loves to take in uranium, but it almost completely excludes lead.
Ah, so it's like starting with a clean slate, a zero lead count.
Exactly. And that uranium, over time, it radioactively decays to form lead. So when we analyze a zircon crystal today, almost all of the lead we find inside it is from the decay of that original uranium.
So it's like a tiny time capsule.
It really is. And to make it even better, there are actually two types of uranium that decay into different isotopes of lead.
So it's like having two clocks ticking away inside the same crystal.
Exactly. Uranium-235 decays to lead-207, and uranium-238 decays to lead-206. And these are two completely independent decay systems. It's like having two separate clocks ticking at different rates inside this tiny zircon crystal.
So you get two independent age estimates from the same sample.
Exactly. And by measuring the ratios of these different uranium and lead isotopes, we can calculate those two ages. And if they agree, it gives us a lot of confidence in the result. And even better, if those two clocks don't agree, if they're discordant, it can tell us that something happened to the zircon later on, like some lead was lost.
And I'm guessing lead loss is a big problem with these super old rocks.
Oh yeah, it's almost always a factor. The article mentioned that these archaeogneisses, almost all of them show these complex histories, including episodes where some lead was lost from those zircons.
So how do scientists deal with that? How do they account for that and still get accurate ages?
Well, this is where the real power of modern zircon geochronology comes into play. In the 1980s, a researcher named Tom Krob made some incredible advancements in how we analyze zircons. He developed much more precise ways to separate and analyze individual zircon grains, and not just the whole grain, but even specific parts of it.
So even tinier than tiny.
Yeah, they could actually abrade away the outer parts of the zircon crystal because those are more likely to have been altered and lost lead over time, and this allowed them to get to the pristine, unaltered core.
Like peeling away the layers of history to get to the original untouched time capsule.
Exactly, and by carefully analyzing these super clean zircon fractions, they could get much more accurate measurements of those uranium and lead isotopes.
Makes sense. And then the article went on to talk about these super high-tech methods like SEMS and LAICPMS. What exactly are those? They sound pretty intense.
Yeah, those are some pretty powerful tools. They let us analyze the chemistry of really, really tiny areas within a single zircon crystal. I'm talking about spots as small as 5 micrometers. It's hard to even imagine how small that is.
Seriously, 5 micrometers.
Yeah, but it's huge for us because it means we can date different parts of the same zircon. Like, we can date the core that formed first and compare it to the rim that grew later.
Oh, that's amazing. So you can actually see different chapters of the zircon's life recorded within the same tiny crystal?
Exactly. And SIMS stands for Secondary Ion Mass Spectrometry, and LAICPMS is Laser Ablation Inductively Coupled Plasma Mass Spectrometry.
Okay, yeah, I'm definitely not going to try to remember those.
That's okay. But basically, they let us see those different chapters in the zircon's history. Like, imagine you could read the individual growth rings in a tree, but at a microscopic level. That's kind of what we're doing with these techniques.
That's a great analogy. And then the article went on to talk about these Concordia and Discordia diagrams. It sounds a bit like a geological maze. What's the basic idea behind those?
All right, so imagine a Concordia diagram like a curved line on a graph. And this line represents perfect agreement between those two uranium-lead decay systems, the U-235 to lead-207 and the U-238 to lead-206. So if the zircon analysis plots right on this curve, we say it's concordant. It means both of those internal clocks are telling us the same age.
Got it. So far, so good.
But if the data point falls off that curve, it's discordant. And this often means that the zircon has lost some lead at some point in its history, maybe because it got heated up again.
So even if those internal clocks haven't been running perfectly smoothly the whole time.
Exactly. And here's the thing. That discordant data isn't useless. If we have a bunch of these discordant analyses from the same rock, they often form a straight line called a Discordia line.
Okay.
And this Discordia line, it intersects the Concordia curve at 2 points. And often, that upper intersection point gives us a good estimate of the original crystallization age of the zircon.
So even with some damage to the time capsule, you can still often figure out when it started.
Precisely.
And the article also mentioned something called MSWD. What's that all about?
Ah, the MSWD. That's the mean square of the weighted deviates. It's a mouthful, I know.
Yeah, I'll just call it MSWD.
That's what we all do. But basically, it tells us how well a group of age dates agree with each other statistically. So a low MSWD means that the age dates are clustered really tightly, suggesting that those zircons probably all formed around the same time.
All right, that makes sense. So with all this amazing zircon dating technology, who are the main contenders for the title of oldest rock in the U.S.?
Well, the article focuses on 3 main areas where these really ancient rocks are found.
Okay.
First, you've got the Archean Wyoming province.
Okay, Wyoming.
Then there's the Minnesota River Valley subprovince, which is part of the Superior province. And finally, there are the Watersmeet gneisses up in the Upper Peninsula of Michigan.
Right, so Wyoming, Minnesota, and Michigan. These are all places with super old rock.
Exactly. And it's important to remember that these individual rock formations, they're all part of these much larger geological units called cratons.
Cratons.
Yeah, they're these huge blocks of ancient continental crusts that have stayed pretty stable for billions of years. Think of them like the really old, solid cores of the continents.
Okay, that makes sense. So let's start our little geological road trip with the Wyoming province. I remember the article mentioning some seriously old zircons found there, some dating back to 4 billion years. But those aren't the rocks themselves, right?
Right, you're thinking of detrital zircon.
Detroital zircon.
Yeah, those are tiny zircon grains that have eroded out of older rocks and then ended up in younger sedimentary rocks, so they're like little time travelers.
Oh, wow.
And finding those 4 billion-year-old zircons in Wyoming, it tells us that rocks of that age definitely existed there at some point. But we haven't actually found those original rocks yet. They could still be out there buried somewhere deep down.
That's wild to think about.
Right. So the article then focuses on the Sakowee earth gneiss, which is found in the Granite Mountains of central Wyoming.
Okay, the Sakowee gneiss. And the article described it as a foliated biotite trondhjemite gneiss. I have to admit, that sounds like a mouthful.
It does, doesn't it? But basically, a trondhjemite is a kind of igneous rock, kind of like granite, but with a slightly different mineral makeup. And biotite, that just refers to a type of mica that's present in it. And the foliated part means that the rock has been squeezed and heated up so much that its minerals have aligned into layers or bands.
All right, so it's been through a lot.
Oh, yeah, definitely. And these TTG suites, that's tonalite, trondhjemite, granodierite, they're actually super common in these Archean terrains, the really old parts of continents.
Interesting. So what about its age? What have they found out about how old the Sakowee gneiss really is?
Well, they've analyzed the zircons from it, and they found a weighted mean age of 3.452 billion years. So that's the age when that original igneous rock crystallized from magma.
3.452 billion years. That's still mind-bogglingly old.
It really is. But then it gets even more interesting because nearby, in another rock sample in the Wyoming province, researchers found these zircons with a significantly older age, 3.822 billion years old.
Whoa, even older. But those aren't part of the Sakowee gneiss itself, right?
Right. These are interpreted as xenocrysts.
Xenocrysts.
Yeah, they're like little foreign crystals that got caught up in the younger magma, that 3.45 billion-year-old magma, as it intruded into the older crust.
So they're like little hints, little clues about even older rocks that might be down there somewhere.
Exactly. So while the Sakowee gneiss itself is around 3.45 billion years old, those 3.82 billion-year-old zircons, they tell us that there was definitely even older Eoarchean crust in that region. It's like finding little pieces of pottery from a lost civilization that's even older than any ruins we've found.
That just blows my mind. All right, so Wyoming has given us some tantalizing hints of potentially some of the oldest materials in the U.S., but the oldest intact rock they've actually dated there is a bit younger. Now let's move on to the Minnesota River Valley and that famous Morton gneiss. I know it's got a pretty complicated history, but what has modern zircon dating revealed about its age and how it formed?
Well, when they applied all these advanced zircon dating techniques we've been talking about to the Morton gneiss, things got even more interesting, or maybe even more complicated, depending on how you look at it. They started looking at Concordia diagrams, and they found these multiple distinct groups of zircon growth, like different generations of zircons.
Oh, so different ages within the same rock?
Exactly. They found one group with a regressed age of about 3.5N6 billion years, and then another group with a regressed age of 3.360 billion years.
Wow, so it's not just one ancient rock, it's like a mashup of different ancient events.
Yeah, that's a great way to put it. It's like a geological scrapbook. And it gets even more interesting. They also found evidence of these younger zircon rims on some of those crystals.
Even younger.
Yeah, like a third generation of zircons. They found rims dating to about 3.145 billion years old, and those seem to be linked to the intrusion of some mafic rocks nearby.
Mafic rocks?
Yeah, those are rocks that are rich in magnesium and iron.
Okay.
And then they also found another set of rims dating to around 2.595 billion years, which tells us that there was another big event in the Neo-Archean era that affected this region. And this event, it actually caused more zircon to grow.
Wow, so this rock has been through a lot.
It really has. And here's another cool thing they noticed. The zircons from that oldest group, the ones around 3.5 billion years old, they tend to have these really nice, well-defined internal growth zones, like tree rings.
Okay.
But the younger ones, the 3.36 billion-year-old group, they often don't have those clear growth features.
Interesting.
Yeah, and this difference, it suggests that these different aged components of the rock, they were probably all mixed together during this huge deformation event about 2.6 billion years ago. Like, it all got juggled up and squished together.
It's like a geological jigsaw puzzle, piecing together all these different events.
Exactly. So the Morton gneiss, while it's been historically important in the search for the oldest rocks, it's turned out to be more like this complex archive of multiple ancient events, rather than a single super old rock.
All right, so that brings us to our last contender, the water-sweet gneisses up in the Upper Peninsula of Michigan.
Ah, yes, the Watersmeet gneisses.
It sounds like this region is a bit more mysterious, keeping those ancient secrets hidden underground.
It is a bit well hidden. Much of the Millie Old Rock up there is covered by younger rocks and glacial deposits, so exposures are pretty limited.
Okay?
But the Watersmeet gneiss, it's exposed in the core of this dome-shaped structure called the Watersmeet Dome. And this dome, it formed much later during a massive mountain-building event called the Pennachian Orogeny about 1.8 billion years ago.
Wow, that sounds intense.
It was, and this dome structure, it essentially pushed up and exposed some of the deepest parts of the Earth's crust that were involved in that collision.
So it's like a window into the deep past.
Exactly.
And what about the ages? What have scientists been able to find out about how old the Watersmeet gneiss actually is?
Well, initially, back in the 1980s, using the older dating methods, they estimated that it was at least 3.41 billion years old.
Okay.
But more recently, they've done these much more detailed analyses using LAIC PMS on zircons from the Watersmeet gneiss, and it's revealed a much more nuanced picture, kind of similar to what we saw with the Morton gneiss.
So even more complexity?
Yeah, it seems like the deeper you go, the more complex it gets. But anyway, in one of the samples, they found these two main groups of zircons that are almost concordant, meaning their two internal clocks agree.
Okay.
One group was around 2.64 billion years old, which is still pretty old.
Definitely.
But then there was this other, much older group dating back to about 3.6 billion years.
3.6 billion. That's even older than what they found in Wyoming, right?
It is, yeah. But then the article goes on to say that a second sample from the Watersmeet gneiss showed a huge range of ages, from 3.8 billion all the way down to just 1.3 billion years old.
Wow, what was going on there? That's a pretty big spread.
Well, that's because this second sample, it experienced a bunch of other geological events after it formed. You know, things that really messed with the zircons and caused them to lose lead, making them seem younger than they really are.
Oh, so like those resetting clocks we were talking about.
Exactly. And these events included things like intrusion of younger igneous rocks.
Intrusions.
Yeah, that's when molten rock, magma, pushes its way into existing rock layers. So they had this intrusion of the Carney Lake gneiss, which is about 2.75 billion years old. And then another one from the Purison quartz monzonite, which is about 2.6 billion years old. And then there was all that intense deformation and squeezing from the Pennachian orogeny about 1.8 billion years ago. And even the mid-continent rift system, which was active much later, between 1.1 and 1.07 billion years ago, had an effect on these rocks.
Wow, so it's like this rock has a whole history book written inside it.
It really does. It's amazing.
But with all that lead loss and all those events, how do they know how old the Watersmeet gneiss really is?
Well, they have to be really careful and selective with the data. They focus on the oldest zircons, the ones that show the least amount of discordance.
The ones where those two clocks are still mostly in sync.
Exactly. And when they do that, when they do these regression analyses, they get ages of 3.685 billion years and 3.598 billion years for the two samples.
Okay.
But if they really zoom in and focus on the most concordant of those really old grains, they get even older ages, like 3.623 billion and 3.618 billion years.
So that's what they think is the most likely true age.
Yeah, that's the minimum age, because remember, lead loss almost always makes things look younger than they are. So it's at least that old, and it could be even older.
Minimum ages. So just like in Wyoming, there's a chance there's even older stuff hiding nearby.
That's right. And in fact, they found some of those super ancient xenocrysts in the Watersmeet area as well.
Seriously.
Yeah, in one sample, they found 3 individual zircon analyses that were way older than everything else, like 3.822 billion, 3.764 billion, and 3.687 billion years old.
Wow, so Michigan's got those ancient whispers too.
It does, and they're interpreted the same way as those ones in Wyoming, little pieces of even older crust that got caught up in the younger magma.
So those are pointing to rocks that are even older than the Watersmeet gneiss. It's just like those zircons in Wyoming hinted at even older rocks there.
Exactly. And the article even mentions that they found similar things in the nearby Carney Lake life and even in those detrital zircons in younger sedimentary rocks, which further supports the idea that there's this really, really old 3.8 billion-year-old crust beneath Michigan.
Okay, so let's recap for a second. We've got Wyoming with those hints of 3.8 billion-year-old material. We've got the Morton gneiss in Minnesota, which is more like a geologic scrapbook with multiple events. And then there's the Watersmeet gneiss in Michigan with intact rock dated older than 3.6 billion years and those super ancient xenocrysts, just like in Wyoming. So who wins the oldest rock in the U.S. award?
Well, based on all the data in that GSA Today article, it looks like the Watersmeet gneiss takes the cake for now. With those zircons showing near concordant ages older than 3.6 billion years, it's the oldest rock that's been definitively found and dated in the U.S. so far.
Wow, so Michigan takes the crown, but it sounds like this is an ongoing investigation. There's always the chance someone will find something even older, right?
Oh, absolutely. That's the beauty of science. It's always evolving as we get more data and better techniques.
And it's not just about winning the oldest rock title, right? It's about what these ancient rocks tell us about the early Earth and how continents formed. The article talks about the scientific significance of these discoveries.
Exactly. Like finding crust this old in multiple spots across the northern U.S. has huge implications for our understanding of how the continents came together. And it's amazing to think that these rocks have survived for so long through billions of years of geological change.
Yeah, it's pretty humbling,
It
actually.
is.
And there's this idea that the southern part of the Superior Craton where that Morton gneiss is found and the Wyoming Craton, they might have once been connected, right? Like billions of years ago.
Yeah, that's one of the hypotheses. They've got these really similar ages and rock types, which suggests that they were close together at some point.
But now they're separated by a huge distance.
They are.
So how did that happen?
Well, the article mentions this model where the Wyoming province might have actually been south of the Minnesota River subprovince way back when, like 2.1 billion years ago or so.
Okay.
And then there was this massive event, probably some kind of rifting, where the crust pulled apart and then maybe some rotation, and that moved them to where they are today.
Wow, so these huge blocks of ancient crust have been moving around like pieces of a giant jigsaw puzzle.
It's incredible, isn't it? And all those ancient rocks from the Wyoming, Minnesota, Michigan region, they represent some of the oldest continental crust in the U.S., like the foundation on which the rest of the continent was built.
That's a great way to think about it. So to wrap things up, it looks like the Watersmeet gneiss is the current champion at over 3.6 billion years old. But who knows, maybe tomorrow someone will find something even older. And either way, it's all about using those incredible zircon dating techniques to unravel the secrets of those tiny time capsules and piece together the amazing story of our planet's deep history. And it just makes you wonder, what other secrets are still waiting to be discovered in those ancient zircons tucked away in rocks all over the world?
That's the beauty of it all. We're always learning more and covering new pieces of the puzzle. And it's just incredible to think that these rocks, they were here billions of years before us, and they'll be here long after we're gone.
That really puts things in perspective, doesn't it? Thanks for joining us for this deep dive. We'll catch you next time.